In this next video, we're going to look at rational functions. And we're going to look at some of the properties of rational functions, but then we're also going to graph some rational functions. So first I want to recall a few things. Some of these things are things we talked about in other videos, but some of them are things we've kind of alluded to but haven't actually discussed. Okay. So the first is to recall domain. So we said before that the domain is the set of all numbers x which result in a real value for the function. In other words, it's the input values for our function that result in a real number when we evaluate it. For us, what this means in terms of a rational function, if r is some rational function, p over q, where p and q are some polynomial functions, they could be constant or not, then the domain of R is the set x such that q of x, the denominator, does not equal 0, and both p and q are real values. Okay? If q happens to equal 0, then obviously that value is not going to be in the domain, and we would have to exclude it from our set. Okay? The other thing we've mentioned before, but not in as much detail, is our asymptotes. And the asymptotes are going to be useful for rational functions because it does two things. One, it tells us where that function is not defined. So when we're looking at the graph, we can actually see the places where the values are not in the domain. But the other thing it does is it tells the end behavior of our function. So much like our polynomials, we used the degree and the leading coefficients to determine what our end behavior of the polynomial was. Well, in the case of a rational function, because we're now looking at it as p over q, there are two leading coefficients and two degrees, one for p and one for q. So we can use these things to determine what our asymptotes for a rational function are going to look like, which again is going to tell us basically the end behavior. Okay? For asymptotes, we have three different types of asymptotes. The first is the vertical asymptotes, and these are the easiest to find because they usually relate to your domain. So once I know the domain of my function, I'm basically looking at all the places where that q is equal to 0. Okay? And so x equal a will be the line of our vertical asymptote. And again, it's only an asymptote if a is defined, but q of a is equal to 0. Okay, so if I'm looking at my rational expression, it means I actually get a number up here, but then the bottom goes to 0. Okay? For our vertical asymptotes, if I'm looking at a graph, it's just going to look like some dotted line on our graph. Okay, so in this case, there would be our vertical asymptote. One of the things to make note of is I can have multiple vertical asymptotes. And again, it just depends on what my q looks like. Okay? If my q has multiple roots where it's 0, then I'm going to have multiple vertical asymptotes. The second type of asymptote that we're going to look at are the horizontal asymptotes. And these again are lines y equal b, so they're horizontal lines, hence horizontal asymptote, where we can get these two ways. If my p of x has degree less than q of x, so again that means if I'm looking at this polynomial p over q, the degree of the top is less than the degree of the bottom, then b equals 0 is going to be my asymptote. Or, in other words, y equals 0 is my horizontal line that gives the asymptote. So again, on a graph, what we're looking at is that x-axis is going to be the horizontal asymptote. Okay? If p of x has degree equal to q of x, so again over here, if I'm looking at p over q, if those degrees are exactly the same, then b is going to equal p over n, p sub n over q sub n, where these are the leading coefficients of our polynomial. Okay? And so in this case, what we're looking at is, again, y equals some p over q. So it's just some other line. Okay? It's still going to be horizontal, it's just not on the x-axis. Okay? In both cases here, what this is saying about the graph, as we said for the vertical we know it's undefined. So if I tried to sketch in a graph on here, it means that as I get close to the intercept or the asymptotes, the graph is either going to go to infinity or negative infinity. And it just depends on where I am on the graph and what my values are. Okay? So I can have something like that. It is never going to touch a vertical asymptote. If I'm looking at the horizontals, what this is telling me is, again, my end behavior. So as I get further away from the origin, the values are going to get closer and closer to that asymptote. What happens in between? Could be anything. Okay? Same thing here. I could have it where maybe it does something like this. Okay? The one thing to notice is if I'm looking at a vertical asymptote, I cannot cross it because that's where my function is undefined. If I'm looking at a horizontal asymptote, I can cross it. And I could cross it many times. For those of you who are going to go on to take trig, you'll see that many of these trig functions that we deal with may pass horizontal lines multiple times before the end values get close to that asymptote. But again, here you've got to think end behavior. Okay? The last type of asymptote that we're going to look at are the oblique asymptotes. And these are curves in the form y equals f of x, where p and q are divided out. P has a degree bigger than q, and when we actually do the division, the quotient is that f of x. And so that's the curve that is going to be our asymptote. Okay? And so there are a couple different things that you could see here. Our curve could be a linear equation. So instead of just having a horizontal line, maybe we get something that slants. Okay? So this would be a y equals f of x. Or we could have one that's an actual curve. So maybe the degree of f is not 1. And so maybe I get something like that as my asymptote. Okay? In both cases, again, it's looking at end behavior. So I could have a graph that does something like that. Okay? Again, it can cross these asymptotes. It just means that far out, it gets closer and closer to that curve, meaning the y equals f of x. In the case here, same thing. I could have one that follows. Now, the way I've drawn this, there's also a vertical asymptote in here, but again, the blue dotted line, the y equals f of x, would be my oblique asymptote, and the curve, again, follows it as it gets closer and closer to infinity. Again, in here, towards the origin, it may do other things. And again, we need all of this information to determine that. Okay? So before we start sketching some graphs, let's start by finding some domains and asymptotes for those graphs. So in these examples, we're going to look at finding the domain for each of the rational functions, finding the vertical, horizontal, or oblique asymptotes. One of the things to keep in mind as we go through these is that I can have both vertical and horizontal or oblique, but I can't have both horizontal and oblique. Okay? So I may have vertical asymptotes as well as horizontal or vertical and oblique, but I can't have two of the horizontal and oblique. Again, both of those are looking at end behavior, so it's one or the other. Okay? Alright, so in this first example, r of x equals 6x over x squared plus 2, and we want to find both the domain as well as the asymptotes. Okay, and so again for the domain, basically we're going to start by looking at the denominator and seeing if there are any places it's undefined. And in this case, we can see x squared plus 2 is basically defined for all real numbers. So here, our domain is going to be negative infinity to infinity. There are no places that that's going to go to 0. Okay? Which tells us right away that for our vertical asymptotes, there are none, because there are no places that the function is undefined. Okay? In terms of the horizontal or oblique, okay, we note here degree on the top is equal to 1, the degree on the bottom is equal to 2. So this tells us degree on top is less than the degree on the bottom, so we're going to have a horizontal asymptote. And because it's smaller on the top, that horizontal asymptote is going to be y equals 0. Okay? Alright, so let's look at this next example. So r of x equaling 6x squared plus 1 over 2x squared plus x minus 1. Now, here the first thing to notice is it's quadratic and it is not always positive. So here I want to start by factoring this out. So we can think this is 2x and x. We're going to have 1's on both of those, plus 2 minus 1 to get the correct signs there. Okay. So there's our new our new rational expression. So we can see that when we go to our domain, we can't have 1/2 and we can't have negative 1, because those will make that denominator 0. So we have all real numbers up to negative 1, not including it. From negative 1 to 1/2, again not including. And then from 1/2 to infinity. So there would be our domain for the function. Okay. In this case, because we do have places in the domain that are not defined, then we can see that we do have some vertical asymptotes. And they're going to be at those spots that make that denominator 0, as long as the numerator is not 0. Okay, so we can see if we plug negative 1 into the top, it doesn't go to 0. So x equals negative 1 is going to be an asymptote, a vertical asymptote. And same thing with the 1/2. If we plug that in, x equals 1/2 is also going to make the top non-zero. So those are the vertical asymptotes. Okay. Here again, if we look at the degrees, notice this was an x squared and an x squared. So the degree on the top is 2, degree on the bottom is 2. Which means, again, I'm looking at a horizontal asymptote because it's the same. And because it's the same, I need to pull off the leading coefficients. So the dominant term here is going to be the 6x squared as it gets bigger or more and more small. And likewise on the bottom, the dominant term is the 2x squared. Okay? Which we can just write as y equals 3. Okay. For this next example, r of x equaling x squared plus 2 over x minus 1. Okay, here again, we can see that our function has a problem in the domain. I don't have to factor because it's linear, but we can see easily that when x equals 1, this function becomes undefined. So our domain is going to be all values except that. Okay. Again, knowing that point, we can see that x equals 1 is going to be our vertical asymptote. Now for the horizontal and oblique, here we see the degree on the top is 2, but the degree on the bottom is 1. So the top is growing a lot faster than the bottom is, which means I'm not going to get a horizontal asymptote. As I move further and further away, the top is going to be much bigger, and so it's going to keep increasing. Okay? So in this case, I'm actually getting an oblique asymptote. Okay? And again, to figure out what that oblique asymptote is, I need to divide out the polynomial and find the quotient. So here, I'm going to take my x squared plus 2 and divide by my x minus 1. If you want to use synthetic division, that is fine. I'm going to go ahead and just do the long division on this. So we're going to divide out. We'll get an x plus 2. We can add a 1 there to get an x minus 1. Subtracting 2 plus 1 looks like 3. Okay? So here, I don't care about this remainder. All we care about is the quotient. So y equaling x plus 1 is going to be my oblique asymptote. Let's look at one last example. So here again, I look at my function x cubed over x plus 1. We can see the domain. Again, linear in the bottom there. Domain is just going to be where x does not equal negative 1. So we'll exclude that from the set. Which means, again, I only have one vertical asymptote at x equal negative 1. And again, if we look at the degrees, the degree on the top is 3, the degree on the bottom is 1. So again, just like in the last example, my polynomial on top is growing a lot faster than the polynomial on the bottom. So here again, I'm going to get an oblique asymptote. And to find it, again, I'm going to need to divide out. Okay? This one I'll use the synthetic division. So we get 1 for the x cubed, 0x squared, 0x, and 0. And we're dividing out by a negative 1. So we'll get a 1, negative 1, 1, negative 1. Okay? Remember, this last piece is the remainder. All we care about is the quotient. So degree here is going to be 1 less. So y equal x squared minus x plus 1 is going to be my oblique asymptote. Now, for your rational functions, all of the ones you're going to look at in these sections are going to have things similar to this. So I'm going to start by finding the domain, find the vertical and the horizontal or oblique asymptotes. Then we can use that information to get the graphs. Now that we know how to find the domain and the asymptotes, let's use those along with the intercepts to sketch some of these rational functions. Okay, so here's a quick outline of what we're going to do to sketch them. First thing we want to do, just like finding the asymptotes, is to start by finding the domain of the function. Then we're going to find the vertical asymptotes using that domain. Next, we'll look at the horizontal and oblique asymptotes using the degrees of the numerators and the denominators and the leading coefficients with those. Once we have the asymptotes, then we're going to go back and find the intercepts. So remember, set x equal to 0 to find the y-intercepts, set y equal to 0 to find the x-intercepts. Okay? Once we have all of that information, we're going to put that information on the graph. So we're going to sketch in our asymptotes and sketch in our intercepts, and then we can use the behavior of the asymptotes to find the rest of the graph. In some cases, you may not have very many intercepts, or maybe you don't have a lot of asymptotes. So then what you can do is test points to figure out what the graph is doing. Okay? So in this first example, we're going to look at r of x equaling 4x minus 4 over x plus 2. So again, the first thing we're going to do is we're going to start by finding the domain. In this case, the x plus 2 tells me that negative 2 is the only point I can't have in my function. Okay? From there, we know that our vertical asymptote is going to be at x equals negative 2. Okay? Again, that's the one place the function is undefined. Okay? Looking at our degrees, So again, degree on the top is 1, degree on the bottom is 1. So this tells me we have a horizontal asymptote at y equal 4. Since they're the same, we pull off the leading coefficients. Okay. For the intercepts, we're going to again set x and y both to 0 and solve. So when x equals 0, we can see we'll get a -4 over a -2, or 2. And when y equals 0, now this is a nice trick to remember for rational functions. If my y value equals 0, that means I'm setting this equal to 0 and solving for x. But we know the denominator can't equal 0, otherwise it's undefined. So it just means I'm looking at when the top is equal to 0. And in this case, 4x minus 4 is going to equal 0 when x is 1. Okay, so there's our intercepts. So to sketch our graph, we're going to start by putting this information on the graph. Again, always label your graph. Okay, so my vertical asymptote is over here, is at -2. My horizontal asymptote is at y equals 4. Okay. And we have intercepts at 0, 2 and 1, 0. Oh, and that's bad. That's a +2 there, so that should be a -2. Now again, like I said, you can use the end behavior to figure out what's going on with the graph, or the behavior of the asymptotes to figure it out without testing points. That's not always going to be the case, but in most cases you can. This is an example of one where I can just use the behavior to figure out what's happening. So if you remember when we said for vertical asymptotes, it is either going to positive infinity as it approaches the asymptote, or it's going to negative infinity. If I look on the right side of my vertical asymptote, I have intercepts over here, and I know these intercepts have to connect. And because I'm getting closer to my asymptote on this side, I know it's got to go towards negative infinity. Okay. On the other side of my intercept, as I move out towards positive infinity in the x direction, my function's end behavior has to look like my horizontal asymptote. So that tells me from here, I'm going to be increasing closer and closer to that horizontal asymptote. Okay. On the other side of the graph, I don't have a lot of information. There's no intercepts over here. All I have is these two lines. But what I can determine from this is, if I look, I know the graph can't do something like this. Cannot. Why? Well, because in order for it to come from negative infinity to approach this asymptote, I would have to cross the x-axis. And I don't have another asymptote, or intercept.